So what's up mga ka-ChE? It's Kuya Daily here, and I'm back with another chemical engineering thermodynamics lesson. And thank you for all the support that I have received in the last video, the how to use a steam table. So I've taught you how to use the steam table, and now let's continue to our solving problems. So these problems I have obtained them from the third reviewer. So third edition na reviewer for chemical engineering licensure examination by Dr. Serviliano, Olano Jr. and the rest. And then this is published by the Manila Review Institute Incorporated. So they have given us permission to use this book to show their support. They want to send us a physical copy of this book, but I already have this book that I am answering right now. Okay, so and this is actually available in National Bookstore or Lazada or in their Facebook page sa Manila Review Institute Incorporated. So just go to their Facebook page and also sa Shopee or Lazada baka. So thank you MRI for supporting this channel. Okay, so now let's continue to our lesson that we have left off. Okay, so now let's go to this. So if you are answering with me, so it is good that if you are following with me, but if you are not, please, if you want to go through this reviewer like me, I suggest that you buy this reviewer so that you can solve with me. They have given us the values of from the steam table already. So they have been very generous to us to give us these values. Diba? So as you can see, there is steam. So it is actually similar to what we have solved in the steam table video that I have taught you, diba? So it is now at 300 degrees Celsius and 2 MPa. So meaning this is SHV, diba? Superheated vapor, and then it enters a nozzle. So nozzle looks like this, diba? And then with the inlet diameter of 5 cm and a steady flow rate of 0.5 kilograms per second. So if heat is lost at the rate of 10 kilojoules per second, and the steam leaves the nozzle at 200 degrees Celsius and 1.4 MPa, also at SHV, diba? Because there are two given. Determine the outlet diameter at the nozzle. So what we are actually really interested here in the values that we are given is only the enthalpy and the specific volume, or the inverse of your density, diba? So we can use these values to find our outlet diameter of the nozzle. Okay, so let's write let's draw the given in the next slide. So we have this is an SHB or superheated vapor. It's also an SHB. So we have our T1 is at 300 degrees Celsius, and let me write the remaining. Okay, now we have finished the writing the given. So the next step in solving this problem is actually the general balance equation, right? So we have the general balance equation, which is the enthalpy plus the kinetic energy. Kinetic energy is contribution of the change in velocity, and then we have our change in potential energy. So let's multiply that by mass flow rate, and then we have Q plus WS. So let us examine, as I've told you in the last video, we have no moving parts in our system, diba? In our nozzle. Nozzle has no moving parts, so shaft work is automatically 0. And then we have no change in our elevation. Is assuming that the nozzle is at the same level, so the potential energy contribution is 0. And now we'll just only look at the enthalpy and then the uh, change in kinetic energy as the contributor to our general balance equation. Okay, so let's simplify our equation. We have delta H plus 1/2 delta U squared. That's the velocity. So, and then it is Q, diba? So, heat released, which is 10 kilojoules per second. Diba? Now, let's look at the system here. So, we have um, to get the mass flow rate, but we are given the mass flow rate here, right? So let's start with the continuity equation, which is equal, states that the mass flow rate of the inlet is equal to the mass flow rate of the outlet. Okay, so we can represent this as A1 B1 or U1 the U1. That's the velocity at the entrance, and then area at the exit, and then velocity at the exit. So U2. We can we can break the area further. It is as a circular, so maybe we can express mass as a volume over density times the density times the mass flow rate, the velocity, the fluid velocity. Okay, so we can express that as that. So 1, and then the area of the circle, the V2 squared, and then U2. Then we can simplify, we can cancel like terms in the separate side. And then we can also, this density is actually the reciprocal of our VSP, right? Or specific volume. So we can put that in the bottom, so in the denominator. So VSP1, and then we have D2 squared U2 over VSP2. So that's our working equation now. So we have to find our V1 or our U1, right? Our U1, and you can find that through the definition of our mass flow rate. Mass flow rate is equal to rho V, diba? Our density times the volumetric flow rate. But we can break that up further. V times V is equal to AU, diba? AU, our area, and then our velocity, fluid velocity. And then rearranging the equation to find U, we have U is equal to M over R rho A, diba? Or because we are given the VSP1 over A, diba? So substituting, we have 0.5 kilograms per second times 0.1247 and 3 per kilogram over the area of our at the first, diba? So this is U1. So everything here is 1. It's at the first state. Yeah? So this is the 5 centimeters just converted to 5 meter, 0.05 meter, and then we will get the velocity to be 31.95 ms or meters per second. Okay, So that's does not end there yet. We are to find the D2, diba? Dito tangita. So let's go back to the general balance equation. So to find U2, diba? So we must find the a difference of the enthalpy first. This is H2 minus H1. So we will have 83.3 minus 3023.5. So it's equal to negative 220.2 kilojoules per kilogram. Okay, so let's transform that to joules because we are operating in joules, just like the first video that I have shown you. If not seen it yet, I'll put a link in the upper right hand corner in the screen. Go watch that if you can't understand this video. So I'm just going fast through here. So let's go through the solution. 0.5, this is the enthalpy difference, joules per kilogram, plus 1/2 times the U2. We have U2 squared here, and then we have 31.95. Then we have negative 10,000 because we are given kilojoules per second, right? So that's negative 10,000 joules per second. Okay, so solve to find U2. That's 633.58 meters per second. And then you will substitute everything here in our equation, above equation. So that's 5 squared times 31.95 over 0.12 547. This is 12547 there. 547, and then you have D2 squared. You have 633.58 over 0.14302. And then you can get the D2 equal to 1.2 centimeters. Okay, that's letter A in our choices. Okay, that's letter A. So that's it. If you have any questions in this question, just leave a comment below and I will answer it as best as I can. Okay. Okay, let's move on to the next problem. So it is proposed to warm a collector plate with solar energy. So the collected energy is then transferred as heat to a fluid in a heat engine, which turns rejects heat to the atmosphere. So if 200 BTU per hour per square feet of energy can be collected when the plate operating at 190 degrees Fahrenheit, estimate the minimum collector area required for a plant producing 1 kilowatt of useful shaft power. So we are to assume atmospheric temperature of 70 degrees Celsius, and then we are given the conversion of 1 BTU per hour is equal to 0.29307 watts. Okay, so how do we go with this problem? So we have to find area. We have to find the area of a warm collector plate. Diba? So let us draw the system here. So we are to find this area, diba? Let's find that area, and then we are given that the energy per unit area, we can get 200 BTU per square feet, diba? BTU per hour per square feet, and then we are given the hot temperature, diba? Operating at 190 degrees Fahrenheit, or we can transform that to Rankine, just add 460 to it, 600 degrees Rankine. Then we have our TC, the cold temperature here, which is 70 degrees Fahrenheit. Diba? Or just add 460 to it, you have 530 degrees Fahrenheit. Diba? And then we are given that the heat, we are to collect 1 kilowatt. Diba? 1 kilowatt, or we have 1,000 watts of energy in that plate. So how do we go in this problem? So remember, we have our minimum collector area. So that's the keyword there, minimum. We have minimum, or what equation or what system you can think you have a minimum regarding the, if you have a efficiency, and then you have a minimum efficiency of that heat engine, or we can say this solar energy, diba? Warm collector plate. So we can treat it as a Carnot engine, and then you just have to rate it by its cold temperature and then hot temperature, diba? So we can actually use that Q min is equal to work over the Carnot efficiency. Carnot, diba? So in Carnot now, the efficiency, Carnot efficiency actually is equal to 1 minus Tc over pH. Diba? If you solve that, let's do it here. One minus 530 over 650. Then we have our efficiency to be 12 over 65. Na? 12 over 65. And then we can actually put that in our equation here. And then we are actually given the work, diba, or the energy that was produced, which is equal to 1 kilowatt. Or we can actually rename this as W, diba? Because this is the work produced. Oh. So keeping the consistency sa atong units, diba? So let's use this equation. Min is equal to 1,000, diba? 1,000 watts. And then to transform that to BTU per hour, you have to divide it by 29307 watt per BTU per hour, diba? And then we have to divide that by the Carnot efficiency, which is 12 over 65. And then you can get the Q min. Let's write that here. Q min is equal to 18,482.5 BTU per hour. Okay, and then if you get the area, you just have to divide this by R Q over A. Yeah? So 18,482.5 over 200. And then you can get the area 92.4 square feet. Okay, that's it. So the nearest answer to that is letter C. So let's continue to the next problem. So we are asked to find the minimum work. So minimum work BTU required to produce 10 pounds of ice from water initially at 32 degrees Fahrenheit, assuming that the surrounding air is at a temperature of 85 degrees Fahrenheit and the latent heat of fusion of ice is 143.4 BTU per LB. So what we have to do here is just do the Q is equal to MCP delta T. Diba? And then QMCP delta T, and then we have to get our coefficient of performance, which is COP, and then get the minimum work. Okay? Just like that. So we just have to, let's just write our given here. We have the 10 pounds of ice here, are given, and then we have the h-ft², actually the latent heat of fusion, h-fuse the initial, h-fuse. Latent heat of fusion of ice is equal to 143.4 BTU per LB. Then we have to get our TC. The TC is equal to the cold temperature, which is at 32 degrees Fahrenheit. And then we have to add it by we have to add 468 for it to become degrees Rankine. So 482 degrees. So we have our temperature is 85 degrees Fahrenheit, and then becomes 545 degrees Rankine. Okay, so I said earlier that we have to use our COP, diba? COP, coefficient of performance. The coefficient of performance for a refrigerator is equal to the QC, which is heat rejected, ba? Heat rejected the surroundings, and then over the work input. Now it is also equal to the cold temperature over the hot temperature. Hot temperature minus the TC, and then we also have to use the classic equation, MCP delta T. Okay, but now we have to use the h-fuse, so which is m h-fuse. So we have 10 elbs 10 pounds times the 143.4 BTU per LB. This is equal to 1,434 BTU. Diba? So what we have to do now is to input that in our equation here at the COP. Diba? COP. So we have QC 1434. Diba? And then we have work, which is we don't even know yet. And then we have our TC, is equal to 492. And then this is 545 minus 492. Shift solve to find W. W is equal to 154.5 BTU. Okay, so that's letter A in our solution, in our choices. Okay, let's move on to the next problem. So certain process requires cooling of a brine solution continuously from 70 degrees Fahrenheit to 30 degrees Fahrenheit. So the atmospheric temperature is 80 degrees Fahrenheit. So there's an available refrigerator with a power requirement of 40 kilowatts. So can this refrigerator be used as is if 100 gallons of brine is to be cooled per minute? So the density of the and heat capacity of the solution is 1.2 kilograms per liter and 3.3 kilograms per kilojoules per kilogram per Kelvin, so respectively. So we are to answer yes or no, or data is not sufficient. Okay, so we have to test if this refrigerator is capable of cooling 100 gallons per minute of brine solution. So the way you have to do that is to get the work required for 100 gallons of brine to be cooled per minute. Okay, that's the strategy there. So we have to list the givens first. So we have pH, pH, which is equal to 70, 70 degrees Fahrenheit, and let's transform that to degrees Celsius, because maybe it's my personal preference, because most of the givens here are in SI, diba? Here in SI. So I want to work in SI units, but it doesn't really matter actually because the answer is the yes or no. Just matter preference to me. I will transform these to SI units. Okay, so 21.11 degrees Celsius, and then we have actually we can also get the running kind. So as I said, it really doesn't matter which units you use, but be consistent. That's my advice to you. 1 point, and then this is 490 degrees Fahrenheit, and then CP, we have CP, the 3.3 kilojoules per kilogram per Kelvin. So the volumetric flow rate is 100 gallons per minute, diba? 100 GPM. So let's transform that to cubic meter per second. So find this in your Paris, diba? I have taught you where this to be found. That's just in chapter 1. There are a lot of these conversions in chapter 1 in your Paris. Gal dian times 60. So get 6.3083 cubic meter per second. And then we can we just have to transform that to transform that to mass flow rate, ba? We have to transform that to mass flow rate by multiplying it by the density. So is 1,200 kilograms per cubic meter, or 1.2 kilograms per liter. You find out the conversion of that, and then times the volumetric flow rate, you can get 7.57 kilograms per second mass flow rate. Okay, now we'll get the heat, diba? The heat that needs to be removed for us to cool the brine solution, diba? We have QC is equal to MCP delta T, diba? And then plug in 7.57 times 3.3, then the temperature difference. Then you can get negative 555 kilowatts. Okay, and then we have our ref, diba? Our ref here is equal to 40 kilowatts ang atong work, diba? So we need to match if ang ato abang kuan ref is higher or lower than that, diba? So how do we do that? We need to use the COP, or the coefficient of performance, which is equal to QC over W, and then TC over TH TC. Okay, so how we can do that is equal, QC is equal to 555, diba? 552 na. And then our W, and then just have to TC is equal to 490, diba? 490, and then if you get the difference of 70 minus 30, we have 40, diba? And then we have W is equal to 45 kilowatts. So see, if you compare it, our refrigerator needs 45 kilowatts of meaning power, diba? So meaning our 45, diba, our given refrigerator of 40 kilowatts cannot cool 100 gallons of brine per minute because it needs 45 kilowatts. Okay, so it is greater than our given ref. So the answer is no. It's letter B. Okay, so no, letter B. So let's go to the next problem. So we have ice cube. So this is one actually situational problem, diba? We have two problems in one statement. So we have an ice cube initially at negative 5 degrees Celsius and weighs 20 grams and dropped into an insulated vessel containing 100 grams of water at 90 degrees Celsius. So we are asked what is the final temperature of the water after the ice melted and the constant temperature has been reached. So what next is the entropy change of the accompanying process. So I will teach you how to get this now. Okay, so we have to list our givens. So we have given here M is 20 grams of ice, diba? Dahil it is at 5 degrees Celsius, na? The initial temperature, and then we have to heat it to 90 degrees Celsius, and then the mass of the ice is mass of the ice, and then mass of the water is equal to 100 grams. So I have to share few uh, a few you have to memorize these values so that you can just not have a hard time finding this in your Paris. Okay, so for water, so memorize these values. So if it is a solid, liquid, and then gas, so the units are in calories per gram per degree Celsius. So that's the units. So this is 0.5, 1, and then 0.48. So that's actually easy to memorize, diba? And then the latent heats. So latent heats, so meaning this is a fusion, and then this at vaporization. Okay, so at fusion, the units here is at calories per gram na lang. Okay, and then the values here is 80 and 80 and then 540. So that's really easy to memorize. Okay, just memorize this if you have a Q-obscurel na problem. So actually the how to go to this you have to find the temperature, right? So we are given actually a mixture, diba? Ice cube is dropped into an insulated vessel containing 100 grams of water. So our system here, you have to draw the system. So you have a fully insulated na beaker siguro. So here is a water dere 100 grams, and then gihulugan siya og ice cube. Ang palang na ice cube dara nga 5 grams. So eventually all of this will melt, diba? And then it will reach a new equilibrium temperature. So we are asked to find the equilibrium temperature now, or the final temperature of this system, diba? So how do we go that? So we have to have an energy balance or heat balance, diba? So the Q absorbed is equal to the heat released. So I've put a negative sign here to indicate that the heat was released, or it's an exothermic reaction, diba? Okay, so let's list let's list the terms on the left and on the right side, diba? So we have what is the on our two binary mixture, what is the component that absorbs the heat. So it is the ice, di ba? And then what release the heat is the water at 90 degrees Celsius man siya. So it is hotter than the ice. So it is releasing energy, di ba? Releasing heat. Okay? So let us list the terms here. So let's assume that all of the ice melted. So we have mCp delta T. This is the ice inside. This is Mi, and then plus Mi h-fuse, because the ice melt, all of the ice melted, and then Mi, then Cp delta T. And then on the right side we have negative M. This is all the water now. So this is Cpi, so Cpw. And then we have that, okay, delta T. So what are the changes in temperature here? So let's enumerate. So at the solid ice, now solid, let's bring that up to 0 degrees Celsius, and then we will melt it, and then we will raise its temperature. So that's how we do this here. So let's start. So the mass of the ice cube is 20 grams, diba? 20 grams. Then let's multiply that by the 0.5, and then the temperature difference, which is 5, diba? Negative 5 na. So Tf minus Ti. So Tf is 0. So 0 minus 5. So that's positive 5. Plus 20 times the h-fuse, which is 80. Dayon, Mi, which is also the mass of the ice, now at liquid, which is retains also the same mass. So multiply that by the Cp of ice, which is water, which is at liquid, which is 1. And then we don't know yet the Tf. Diba? The Tf, and then it is equal to 0. The initial temperature is at 0. Okay? And then we have to get our with the right side of the equation, we have negative 100, diba? So 100 grams, and then 1, the Cp of water in liquid, and then Pf minus 90. Okay? Temperature final minus temperature initial. And then shift solve to find Tf. So you can actually find Tf as 61.25 degrees Celsius. Okay? So that's actually letter A. Letter A in our choices here. And then we are asked for the entropy change in joules per Kelvin of the accompanying this process. So in order to solve this is 29, and then we have to go 30 here. We know that this we have to assume that this process occurs at constant pressure. Constant pressure. Then I actually don't have a derivation to this, but the we have to find the change in the entropy of both, diba? Sa entropy sa water and the entropy sa ice. So memorize this equation. So memorize this equation. So for the ice, so Si, so Si, so you have a Cp ln T2 over T1 plus the h-fuse, and then we have divided by the T2, and then plus Cp, the ice at the water at liquid, and then ln T2 over T1. So how do we do that? So Si, so this is the ice, but Cp of ice is 0.5, di ba? Then Ln, we have to use the degrees now. So T2, which is 0 degrees here, di ba? 0 degrees here, which is this is equal to 273 Kelvin. And then T1, which is the negative 5, di ba? So you can 268, di ba? T1. Then h-fuse is equal to 80, and then divided by the T2. Na. Then have Cp, diba, which is actually 1. Then Ln, the new temperature now that we are going to we got, diba, the 61.25, just add 223 to it, then you can get 334 point, actually we can get this Tf, then Ti 34.25, so that you will not be confused, and then divided by 273. Then you can get the entropy of the ice, diba? At 0.5047 cal per gram per K. So multiply that by the mass of the ice times 20 grams, diba? And then transform calories to kilojoules because we have or joules because we are asked in joules, diba? The unit in joules. So just multiply that by 4.184 joules, then it's the conversion actually, and then you will get 42.23 joules per Kelvin. Okay, so that's for the ice. Then for the water, it's actually simple, ba? SW. So it's just Cp, Ln, T2, or Tf, or Ti. So that's 1 times Ln. So we have 334.25 here, and then we have 90 plus 273, which is 363 Kelvin. We'll get SW is equal to negative 0.0825 cal. Same units, cal per gram per Kelvin. Transform that to let's transform that to joules per kilogram. Multiplying it by the mass of the water. So 0.0825, which is negative, times 4.184 times 100 grams. You have SW is equal to negative 34.52 joules per Kelvin. Okay, so to get the overall change of the system, we have delta S equal to Si plus SW. So let's add the two values, 52, then you will get 7.81 joules per Kelvin. Okay, and that's letter A. That's letter A in our choices. Okay, so that's how you get the entropy change of this accompanying process. Okay, so now let's go to next problem. Actually, it's the third to the last problem that I will give you. Okay, so calculate the change in molar Gibbs free energy of liquid water treated as incompressible fluid when pressure is increased from 1 bar to 2 bar at 280 198 Kelvin. Okay, so this is really easy. So let's just uh, um, list the given first. Bar, and then we have our temperature, di ba? Which is 298 Kelvin. So we just have to find the right formula for this. So change in molar Gibbs energy is actually equal to um, uh, RT ln P2 over P1. That's actually that easy. So just have to find just to substitute, diba? Then R it's actually in your calculator, diba? 3.18 8.314, and then uh, ln 2 over 1, diba? P2. It's 2 over 1, and then we'll get 1,000 joules per mole, or 1.72 kilojoules per mole. Okay, so that's letter B in the choices. So I forgot to write the choices here in the presentation, but this is letter B. This is letter B in the choices. Okay, so that's actually it's actually easy. That's the easiest one that I have given you. So let's continue with the last problem that I'm going to give you this time. So we have a problem here. So steam at 300 degrees Celsius. So 300 degrees Celsius, and we have two values here, diba? So this is a superheated vapor, and then it enters a turbine, diba? So it enters a turbine. So turbine na, so it has a moving part now, so it's not a nozzle anymore. So it have rate of this is the mass flow rate, diba? 5 kilograms per second, and then it's well insulated and operates a steady state. So well insulated, and then the steam outlet pressure is 0.7 MPa, and then using the following data, so calculate the following. So we are given here the data. So, and then we are to calculate the work obtained from the turbine if the process is isentropic. And then if it is if we are given the specified temperature is 255 degrees Celsius, the same outlet pressure, what is the isentropic efficiency of the turbine? Okay, so let's go. Let's solve this. Okay, so we'll have to draw the given first. So in every problem, just have to really draw the problem, diba? So here, as you can see, you have a turbine, diba? So have a turbine. So not the the figure is now reversed, diba? So because we are extracting energy from it, not putting energy to it. So the first state is at h-ft², diba? And then at the second state, as you can see, there is only one, diba? So na lang ka-pressure dihatag. So that means this is at saturated vapor, diba? Saturated vapor, saturated liquid. Let's put all the given here. So now that's given that we have already written the givens here in our system. So the first thing is that we have to know the process. So we're given that the process is isentropic, diba? So meaning what if isentropic means there's no change in entropy, diba? So meaning the S1 is actually our S2, but to indicate that this isentropic, we have to put a prime there. So S2 prime. So meaning this is actually equal. So S1 is equal to S2 prime. So the next step dayon is to find the quality of this steam, diba? Quality of this steam at 0.7 MPa. So, and this is the isentropic quality of the steam. So you have to find the S. I have no better way of representing this, but let's just name this SL, and then SV, SL. I don't know if these are liquid or vapor, but I just named them that, and it actually fits. So S2 is equal to 7.1229. And then what are SL, SL and SV? So if we go back to our problem, diba? So what I would like to name as SL is actually this one, the lower value, and then this is the SV, the higher value. Okay? So SL is equal to 7.1053. Then SV is equal to 1455, 7.1053. Then get the quotient. You have 0.438. Okay, and then you have to find the isentropic pod nga enthalpy, diba? So isentropic pod nga enthalpy, which is H2, using our isentropic quality. So how do we do that? It's just HL, then plus X prime, and then HB minus HL. Okay, so again, this is HL, then this is HB. Okay, so the lower and then the higher. Okay, so we have H2, HL is equal to 2953.6 plus 0.438. Then you have 174.9 minus 2953.6. Then you can get the isentropic enthalpy, the second state. You will get 2962.93 kilojoules per kilogram. Okay, and then we are asked to find the isentropic work, diba? Isentropic work. So the isentropic work, we have the isentropic work. Just multiply the mass flow rate, and then H2 minus H1, but this is actually a H2 prime, diba? So, and we got H2 prime already. So we have 5 kilograms per second, and then just multiply that to 2962.93 minus 3051.2. Then you will get the isentropic work to be negative 441 kilowatts. This is letter C. Nah? So it's actually near to 442 kilowatts. And now let's go to the last problem, which is number 34. So we are given the specific temperature of 255 degrees Celsius. So let's interpolate. We can interpolate now the because you're given the exact temperature, we can get the proper value of the enthalpy and then entropy now. Okay, so can do a linear interpolation to this. So you can get the H2 is equal to 2964.25 kilojoules per kilogram, and then the S2 now is equal to 7.1254 kilojoules per kilogram, Kelvin per Kelvin. Okay, just interpolate between these two values. Okay, and then you will get that the values that I have given you. Okay, that's what I did. And then go through the same process again. So this is at 34, diba? Go through the same process again. Get the isentropic quality of the spin at the outlet. So we have S2, diba? Which is equal to isentropic man, isentropic. So this is S2 gihapon. SL, and then SB, SL. And then this SL is actually equal to the S2 that we got, diba? Oh no. This is actually magapon, same magapon. SB. Oh no. This is S2, diba? This is S2 now. So this is S2. S2 prime and then S2. So S2, so you have S2 prime, which is 7.1229 minus 7.1053 over, we have 7.1254, and then 7.1053. We will get 0.876 quality. And then get the enthalpy, isentropic entropy. So the same hapon, same kini niya formula gapon, but let's write the formula na lang. X prime, then H2, this is H2 minus HL. H2 is equal to 3.6 plus 0.876, and then kini 2964.25 minus 2953.6. You will get 296. This should be the same. 2962.93 kilojoules per kilogram, ba? 62.93. So you will get the efficiency, di ba? Isentropic efficiency of the turbine. So the isentropic efficiency of the turbine is equal to the work at true conditions, and then the actual conditions, the actual, then over S shaft work isentropic. Okay, so and then just multiply that by 100 later. So the work now, so here, so we have the actual, the actual. So we have 3051.2 minus 2964.25, which is the actual, ini actual, over 3051.2 minus kini, your isentropic enthalpy, 962.93. You will get just multiply that by 100. Then you will get 98.5%. Okay, so that's letter D in our choices. Okay, so that ends our uh, chemical engineering thermodynamics lesson for today. I hope you find this helpful, and please share this to your friends. And please don't forget, if you want to review with me, please buy the this book. So the reviewer for chemical engineering licensure examination, I've got these questions from here. They have great compilations of past board exam problems here, and you can buy this at any can buy this at NBS or Shopee or Lazada. So a big thanks, super big thanks to Sir. Shout out kay Sir Lowen, who helped me, and then also to Daniel Joshua Beha, who helped. Also, I've given these problems to him, and this solved these problems with vigor. Diba? So he asked me what he did wrong, and then we had a great time solving these problems, and I hope you had a great time solving these problems too. Okay, so that's it for this week's lesson, and please keep on watching my videos, and please subscribe. And then I want to thank you all for supporting my channel. So we are now at 391 subscribers. So thank you for all your support, and please we will reach 1,000 subscribers hopefully by before October. So please help me reach that, and please help me stream my videos, because I still have 2,500 watch hours more to go for us to monetize this channel. So please help me with that. So I hope you found this problems helpful, and please share this to your friends. Okay, don't forget to like and subscribe. And today that's it for our lesson today. Bye bye, annyeong.